So now that we've looked at the implementation of Search with Parallel Streams, let's go ahead and evaluate that version and compare and contrast it with the earlier sequential version, and then see what's still missing that we can improve on with later implementations. So let's take a look at the pros first. So the difference between sequential and parallel is absolutely minuscule, which is the whole point. We have the sequential version, which uses stream. We have the parallel version, which uses the parallel stream. That's the only difference. That's cool. So you can get these great speedups with little or no effort on your part. Here's an example of the speedups, which we got with little or no effort on our part. We were able to go from roughly 2,000 milliseconds to process everything to roughly 450 milliseconds to do the whole processing. And that was on a quad-core processor with hyper-threaded cores. And it's a good speed up. It's basically a linear speed up, actually sort of super linear speed up because it's hyper-threaded, but it gives us everything we need. I also ran a version of this on my earlier quad-core MacBook Pro. I now have an 8-core MacBook Pro, but back in those days I had a quad-core MacBook Pro with less memory but faster processors. So you can see the processors on the Mac were a little faster, but not quite as much memory. And so as you would expect, the processing time is actually lower, which is good. It means it took less time to process stuff because the processors were a little faster. We got the super linear speedups because of the use of hyper-threaded virtual cores. So you can learn more about hyper-threading if you look at the link at the bottom of the page. But basically what hyper-threading does is it uses something called superscalar processing, where you can actually execute more than one instruction during a clock cycle by simultaneously dispatching multiple instructions to different execution units. So it's not quite as efficient as having more cores, but if you play your cards right and the underlying virtual machine and the underlying compiler and assembler and then the whole tool chain in the system is done right, you can end up getting super linear speedups in the number of cores because you're able to get a pipelining optimization. So you can read more about that down here. It's kind of orthogonal to the topics of the course, but it's a good example of how you can wring out every nanosecond of performance if you're willing to attack parallelism at multiple levels within the overall system stack. But of course, not everything is unicorns and rainbows. So just because we only have 2 minuscule changes to the code doesn't mean it's the best way to do things. And in fact, there's other ways to get speedups that are even more efficient than the simple approach we used here. Now, if you take a look, they're not wildly better, but they are better. So what this indicates is that sometimes if you really want to wring out every last ounce of performance in your system, you may need to go beyond the obvious. And so we'll talk about that when we get into other variants of this. Now, naturally, as they like to say with gasoline mileage advertisements, your mileage may vary. So it's not always the case that you'll get the performance results that I show you here. So that's why you have to go out and benchmark your code and set it up properly so you get apples to apples comparisons that will fairly evaluate the pros and cons of different approaches. We will later, probably next week at this rate, talk about the Search with Parallel Splitterator class. And that's an even more aggressive way of doing optimization and parallel processing. So you'll see that it actually does parallel processing in 3 dimensions, not 2. So it does parallel processing on a per work of Shakespeare level, parallel processing on a per phrase level, and then it takes a given work of Shakespeare and it chunks those things up and does the searches in parallel within a given work of Shakespeare. So we'll see later how that works. It's very clever, requires some more powerful splitterator logic to make everything work, but it demonstrates that if you put your mind to it, you can really get amazing performance without an enormous extra amount of work. So that's the end of the overview of our parallel search stream gang program, or one of the variants of that. We'll take a look at other variants later. But I want you to really come away with this with a good feeling that parallel streams often get you where you need to go. And only if you don't quite meet your performance objectives is it worth taking a look at the more advanced capabilities we're going to talk about in upcoming lessons.